Hello, welcome to Chapter 5, Section 5. Today we are doing normal curves for binomial distributions. So we are still on normal curves, so we still need our table and all that good stuff. But because today is about binomial distributions, this is something that we've done in the past when we did probabilities of binomial distributions. But now we're finding probabilities of binomial distributions using a normal curve instead of the formulas that we had back then. So just like last section, we're going to have to find a new mean and standard deviation of the binomial distribution. Kind of like that standard error formula, but this time, because it's not a sampling distribution, it's not called a standard error anymore. It's just a standard deviation of a binomial distribution. And so how you're going to know that it's going to be a binomial problem is that there was always, if you think back to what binomial probabilities were, we were looking for probabilities of something happening a certain number of times within a certain number of trials. So remember, there was like a total number of times you did something and we called that n, and then they were asking about like what is the probability that you get exactly 5 successes or something like that out of the 10 tries or whatever numbers. So that's the type of problem that we're trying to do. This time though, using a normal curve, we need to figure out the mean and the standard deviation. So the formula for the mean is n times p. So n being the total number of times you did something, p is that probability of success. And then the standard deviation formula is going to be the square root of n times p times q. So this time around when we figure out our normal curve or set up our normal curve, we have to find both a new mean and a new standard deviation. For the standard deviation, the q just stands for the probability of failure. And remember, we can find that by doing 1 minus p, because if p is success, then 1 subtracting p is like the probability of you failing. Okay. And then the shape of the binomial distribution, kind of like before, we kind of have to check to make sure that it's actually going to be a normal shape. So to check for that, it's a different method of checking for it. When you do n times p, you have to make sure you get a number greater than or equal to 5, and n times 1 minus p also has to be greater than or equal to 5. If either one of these equations isn't true, then it is not a normal distribution. So if it's not normal, when either one of these equations is not true, then you can't do the problem at all. So, I mean, kind of a good thing. All right, so let's say, for example, we want to see whether we can use the normal distribution to approximate x, the number of people who reply yes. If you can, find the mean and standard deviation. So in this first example, we have 62% of adults in the U.S. have HD TV in their homes. I think this is a lot more common nowadays, but you randomly select 45 adults in the U.S. and ask them if they have an HD TV in their homes. So here, our sample size, our n, is 45. So that's kind of like our number of trials as well. And then they also said 62% of adults have an HD TV in their home. So that's the probability of success. So p for us is going to be 0.62, because remember, we always want to change our percents into decimals before we do anything with the problem. Okay, so p is 0.62. I'm also going to find q while I'm at it. So 1 minus 0.62 is going to be 0.38. Okay, so now we need to see if the normal curve actually works. So if I do n times p, I'm going to get 45 times 0.62, and that ends up being 27.9, and that's definitely bigger than 5. So good. That one works. And if I do n times 1 minus p, then I have 45. 1 minus p we said was 0.38. When I multiply that together, I get 17.1, which is also greater than or equal to 5. So that means this is actually going to be a normal curve. Cool. I can draw that out. The mean then is just n times p. So remember, our formula for the mean is n times p, which we did. We did that when we did our first check for the normal curve. So 27.9 is going to be our mean. And then for our standard deviation, we have to figure out the square root of n times p times q. So plugging in my n of 45, p of 0.62, and q of 0.38, and then square rooting the whole thing, I end up with 3.256. And again, here for our standard deviation, if you end up with decimals, it's more accurate with more decimals, so you want at least 3. And then in your homework problems or classwork problems, you might see it specify how many decimal places they actually want, but we usually want to be more accurate. So anything we do in this class, you'll want at least 3 decimal places. Okay, another example. So this time 12% of adults in the US who do not have an HDTV in their home are planning to purchase one in the next 2 years. You randomly select 30 adults in the US who do not have an HDTV and ask them if they are planning to purchase one in the next 2 years. And again, we want to see if a normal curve would fit for this. So to check for that, we need to multiply n times p, n times 1 minus p, and see if we get a number bigger than or equal to 5. So in this problem, we are told that 12% is our probability of success, so P. And then they also say we're selecting 30 adults, so that's N. So N equals 30, P equals 0.12. So that means Q would be 1 minus 0.12, which is 0.88. Okay, and so now I'm going to check N times P. So 30 times 0.12, I end up with 3.6. Oh no, 3.6 is not a number bigger than 5. So right away, since n times p does not work, then this is not going to be a normal distribution, and we can't even find the mean and standard deviation anymore. So all of that is just out the door. We can't do anything. Sometimes you'll see problems where n times p is greater than 5, but then n times 1 minus p is not greater than 5. So even then, since one of those two rules was broken, then you still can't use the normal curve. Okay, so now I want to do an example where we're actually finding probabilities now. So in this problem, 62% of adults in the US have HDTV in their home. You randomly select 45 adults in the US and ask them if they have an HDTV in their home. What is the probability that fewer than 20 of them respond yes? Okay, so the setup of this, we kind of have a good idea of now, because we just used all these numbers in part A of our previous example, and so we know a normal curve would fit. And we also already know our mean is 27.9, because we did the n times p, and we know our standard deviation is 3.256, because we did the square root of n times p times q. And then here, we're asked about a probability that fewer than 20 of them respond yes. So here's where it's kind of weird and a lot of bit different. So in this section, when we talk about binomial probabilities, anytime we were asked about these probabilities, the numbers that we can be asked about, 20 or whatever number is in the question, they always had to be whole numbers, because you had like a whole number amount of successes. And so when we find our probabilities, it's kind of awkward, because sometimes if we did fewer than 20, we wouldn't actually include the number 20 when we wanted to. And so there's a new rule that we have to do when we use our normal curve. It's going to be either add or subtract 0.5. The add or subtract 0.5, you have to decide whether you are adding or subtracting. You're not going to do both. But because of that, we need to determine, based on the wording of the question here, whether we are adding or subtracting. So here we are asked about fewer than 20. Fewer than 20 means like less than 20. So less than 20 means we don't include the 20 at all. Anything below 20 is what we actually want. So the add or subtract 0.5, if I were to add 0.5 to 20, I would get 20.5, and that's not a number that's less than 20. So here, if I subtract 0.5, I would end up with 19.5, which is a number that's less than 20. So in this case, I would subtract, because I want to end up with a 0.5 number that actually fits the fewer than 20 words that they're saying. So that means in my normal curve, the number that I'm actually looking for and shading from is going to be 19.5, because I've subtracted the 0.5 from 20. And we'll do more examples so you can kind of see like when you add, when you subtract. But for this problem, we're doing fewer than 20, so we shade to the left because that's less than, and then we're using 19.5 because that's the number that's less than 20. Basically, whatever number they're asking about in the question, it's not going to be the number you're going to use. You always have to either add or subtract 0.5 before you do your problem. So once we've shaded that in, we can find our z-score. This part is the same as usual. So 19.5 minus our mean of 27.9 divided by our standard deviation of 3.256. When we do that in the calculator, we end up with negative 2.58. And then when we look in the table for our percentage of negative 2.58, we end up with 0.0049. So that will be our probability that fewer than 20 of them respond yes. Okay. So the hardest part of this problem was determining whether we add or subtract 0.5, because everything else was kind of stuff that we've done before. So I kind of want to talk a little bit more about that. So in this problem, we said fewer than 20, or if, sometimes you'll see it as less than 20. So if it was less than 20, we would have subtracted and used x equals 19.5. X being that number that we're using to draw in our picture and shade. Okay. Let's say the words in the problem said like more than 20 or over 20, something like that, whatever words mean more than 20. More than 20 then would be that we would need numbers when we add or subtract that's more than 20. So if I subtracted 0.5 and got 19.5, 19.5 is not more than 20, so I wouldn't be subtracting. Instead, I should add, because if I add 0.5 to 20, then I would get 20.5, and that is a number that's more than 20. So here, we would add. Other words that you might see in the problem is like at least 20. And in our math symbols, at least 20 would be greater than or equal to 20. So since we're talking about greater than, we would have used 20.5. But because it can also equal 20, then we need to make sure that 20 also gets included in our shading. So if you shade because at least 20 greater than or equal to, we would be shading to the right. But if you started at 20.5 and shaded to the right, 20 wouldn't actually be included in your shading. So instead, if I start from 19.5 and shaded to the right, then 20 would get shaded and any numbers bigger than 20 would get shaded, which is what we want with at least 20, 20 or more. So when it's at least, we would end up subtracting the 0.5. And lastly, if it's less than or equal to, the words are usually at most. Then at most 20 means that we would want 20 or less, because the highest it could be is 20. So in this case, we would want to shade to the left of 20, but also include the 20 in our shading. So if I use 20.5 and shade it to the left, then 20 does end up getting shaded. And so anytime it's at most, you're going to add 0.5. So these are kind of like the rules of when you would add, when you would subtract. Okay, in this last example that I want to do, we have a survey reports that 62% of internet users use Windows Internet Explorer as their browser. I'm really hoping this number is way down now because this study was from a while ago. But I don't know who else is still using Internet Explorer anymore. I don't even think Internet Explorer is a thing anymore. Like, didn't they change the name? I don't know. You randomly select 150 internet users and ask each whether they use Internet Explorer as their browser. What is the probability that exactly 96 will say yes? What the heck? In this question, they don't even give us like a less than, greater than. They're asking for exactly 96. This is different. What the heck? So in this case, anytime you see exactly 96, this is when you do both add and subtract 0.5. Okay, so for this problem, we want to make sure first that it's actually going to be a normal curve. So we're going to have to test out n times p and n times 1 minus p and make sure that they're greater than or equal to 5. So in this problem, n is going to be 150 because they asked 150 internet users, and they also told us p is 62% or 0.62. So that means q would be 1 minus 0.62, which is 0.38. Okay, so from here, when we check our n times p, 150 times 0.62 ends up being 93, which is way bigger than 5. Great. And then n times 1 minus p, so 150 times 0.38, is going to be 57, which is also greater than 5. So good. We know this is going to be a normal curve. The mean is going to be 93 because that's n times p. Our standard deviation is n times p times q, which is 150 times 0.62 times 0.38, which is going to be 5.945. And again, notice that I'm using at least 3 decimal places. And so for this problem, the place that we're shading, if they want exactly 96, well, 96 is like over here on the right. We're going to add and subtract 0.5 because that'll give us 95.5 and 96.5. And we are looking for the area in between, because the area in between is where 96 is, and that's the part that's shaded, which is what we want. So anytime it's asking for exactly a number, this is an in-between problem, and then you are finding the area in between the plus 0.5 and the subtract 0.5 numbers. So let's find our two z-scores. I'll start with the bigger one of 96.5 minus our mean of 93 divided by our standard deviation of 5.945. And then my other z-score will be for the 95.5. Okay, so the z-scores that I get are going to be 0.59 and 0.42. And then we would use our table to look for the percentages of both of these numbers. For the z equals 0.59 on the positive side, we get 0.7224. And for 0.42 as a z-score, we end up with 0.6628. And so remember, with our in-between areas, we would subtract our two percentages together to get 0.0596. So that will be our probability for this one. Okay, so just to recap, if the problem says less than, you subtract the 0.5. Greater than, you add the 0.5. At least, you subtract the 0.5. At most, you add the 0.5. Exactly is when you do both. Add and subtract the 0.5 and find the area in between. All right, that's it for this section, and that's it for this chapter because this is the last section of chapter 5. Thanks for watching. Don't forget to like and subscribe. Bye.